Welcome! In today's video, we are going to explore some of the techniques involved in analyzing noise and vibration data from rotating machines. Let's start by loading our data. In the Examples folder, we have our data file called Race Car Run Up. This contains engine data from the exhaust, as well as microphone data. As we load our data, you'll see vibrations increase as the engine revs up. We begin by deselecting the signals we don't need, and leaving the signal we want, which is the exhaust signal. We start with a basic frequency analysis, like the auto spectral density with the default parameters. Let's look at our results. As expected, this type of analysis won't reveal much. We know that our engine has gone through a range of frequencies. As it is accelerated, so this type of analysis isn't suitable. We are going to do a different analysis. We will be choosing the hopping FFT and set our parameters. You'll notice that the graph has changed slightly. At the bottom of the graph, the x-axis still represents frequency, but now the y-axis shows us the time. Instead of a single curve, the graph now has a range of frequency spectra. What we are doing is investigating how the data's frequency alters over time using FFT analysis. Let's change the view to an intensity plot and put this on a log scale. When the engine speeds up, we can observe that the frequency analysis also rises. This is evident on the lines shown on the intensity plot. What's still lacking on this graph is information about the engine's speed. While we can see when events happen and in which lines, we don't have the data on how fast the engine is moving. We'll focus on that next and see how it relates to speed. Let's explore how to analyze the data in the frequency domain while taking into account the engine's speed. There are multiple methods for engine speed measurement. The most common way is to utilize a tacho signal. Let's return to our initial data and select a different signal known as tacho. The tacho signal shows time data recorded alongside the vibration and noise data, allowing for simultaneous analysis. Tacho signal can be generated in various ways. For example, optical techniques or something connected to the electrical system. Let's zoom in on this section. This graph represents a tacho signal. For every revolution of the engine there are a number of pulses. Since we are looking at the start of the signal, these pulses are evenly spaced and not much is occurring. If we scroll further along the signal to when we know the engine was running at a much higher speed, we can see a substantial increase in pulses that indicate the engine is rotating faster. This data can then be used to help us determine how the engine's speed changes when we move through time. In this dataset, we will select the signal called tacho speed that has been previously analyzed, likely generated from one of the analyses. If we look at this signal, we see the same time period as the acceleration of the engine. This signal tells us about the speed at a particular time. For instance, at 2 seconds, we can see the speed is roughly at 2,500 RPM, so we can see the engine accelerating in time. Since we have acquired the speed information, we will now look at a different type of analysis called the waterfall. Let's go ahead and unselect the tacho and speed signals since we do not need them. We will focus on just looking at our original exhaust data and do the waterfall analysis. Let's set our parameters. Let's check that the signal we currently have with the data is called tacho. We then ensure that it is 2 pulses per revolution. For our waterfall analysis, we would like to start at 1000 rpm to 6000 rpm. We would also like spectral lines every 50 rpm. Now we have a new graph. At first, it looks a bit like the hopping FFT graph previously. But if we turn on all the lines, we can see the difference. The x-axis still represents frequency, but on the y-axis, we've replaced time with speed in RPM, revolutions per minute. We can see the lines which were curved before are now straight, directly relating this to the rotation of the engine. As the engine speeds up, these harmonics get stronger. If we now change the view to an intensity plot, then put it on a log scale, we can see clearer lines. These lines are often known in rotating machinery as orders. In this instance, because we have a 4-cylinder 4-stroke engine, the second order is the dominant one, as shown on our graph here. Let's enable these order lines to make these orders more visible. This allows for clear labeling and visibility of these orders. So, this is how we analyze our speed. We have also produced a waterfall plot. The next step for us is to extract order information. We've finished our waterfall analyses and we can see that we have ended up with our frequency versus speed map of our waterfall plot, which we have identified the orders. The next thing to look at is how we can look at these orders in more detail. We'll now explore another analysis titled Extract Nominated Orders and Overall to extract specific orders. Let's set our parameters. We will start the order at 2 with the order increment of 2. We are interested in the even orders here as it is a 4-cylinder 4-stroke engine and 4 orders. So we will get 2, 4, 6, and 8. We are also going to extract the overall level from the data. Let's view our new graph. We will select all of the signals to show us the results. As you can see, we have our orders and the overall level. The overall level represents the total vibration coming from our engine for the measurement we made on the exhaust. This top black colored-in line is our overall level. As per expectation, as the speed increases, then the vibration also increases. Let's add a legend so we can be sure we know which order is which. We will also make the overall line bolder so it stands out. As you can see, the blue line here, which is the second order, makes up the entire noise, and is almost as high as the overall line. Further along the speed range here, we can see the red line, which is the 6th order and peaks for a while. Then, here is the green line, which is the 4th order. We can see we have a very high peak. Why are orders important? Well, in the context of automotive applications like engines, orders help us understand the source of noise and vibration. Some orders are desirable, while others are not. For instance, we might want to increase or decrease specific orders to achieve a sportier sound. Alternatively, in other applications, certain orders could be harmful and can cause damage. In such cases, we aim to reduce these orders during the design phase and measure their impact here. This is how we extract and utilize orders to meet our objectives. We hope this has given you an understanding of how rotating machinery in DATS works.